Hello and welcome back. So today we are talking about finding volumes using the disk and the washer method. You've found volumes before, of course, during geometry, but now we're going to use a calculus-driven method to actually find volumes of a rotation around an axis. So here we have the equation x plus 3y equals 6, or y equals negative 1/3 x plus 2, x equals 6 minus 3y, and we've graphed this here. And so you can see we've got this big space, and I'm going to call that r. And if we rotated r here around the y-axis, I'm going to just draw a little like arrow to indicate that that's rotating. If we rotate that around, you can see that we're going to end up with a cone. And we could actually use the regular volume of a cone to find the volume of it, that formula, v equals 1/3 pi r squared times the height. We could do that, but we're going to actually use calculus methods to find this volume. So here you can see what we're going to think about is having like cutting out a slice or a disk. This is a disk that we're talking about in the disk method, and using that plus integration to actually calculate this volume. So if we slice out a little disk here, we've got our radius is going to be x, and our height is going to be dy, right? We're taking that with respect to y. So you can see that here we've got x and dy. So we can actually find this volume. We can actually write down what this is going to be. So our volume of the cone would be, well, our volume of the cone from 0 to 2 is going to be equal to pi, right? Because of course it still involves pi, times the square, or the integral, excuse me, from 0 to 2 of x squared, our radius squared, dx, okay? Well, we can rewrite that because this is perpendicular to the y-axis. I want to use this with dy. So this is going to be equal to pi times integral from 0 to 2 of 6 minus 3y squared. And I already have that up here. That's where I got these equations from. Dy, which is equal to pi times the integral from 0 to 2 of 36 minus 36y plus 9y squared dy. And I can solve this. We've got pi times 36y minus 18y squared plus 3y cubed from 0 to 2. So you're going to have pi times 72 minus 72 plus 24. So our answer, the volume of this cone, is 24 pi. Okay. So when we're looking at what the volume of a disk is, the volume of the disk is going to be equal to the area of the disk, right, times the width of the disk, or you could say the height, you know, depending on how you're orienting the disk, I guess, right? So the volume of the disk up here is going to be equal to the area. Well, the area of this disk is pi r squared, right? So that's why I use this x squared here, pi times r squared, times the height is going to be dy here, right? And so I actually put this in terms of y so that I could use dy. Good? Okay, let's actually go through some examples, and I think you'll be able to see this a little more clearly. So we're asked to set up and evaluate the integral that gives the volume of the solid by revolving the region about the stated axis. So here we have y equals negative x plus 1. We want to rotate that about the x-axis. So if I graph that, I'm going to have oops, can you see that? Yeah, okay. I graph this. I'm going to have an intersection point at 0, 1, and I'm going to have an intersection point at 1, 0. And this is the equation y equals 1 minus x, or x minus negative x plus 1, whatever you want to say. And if that rotates about the x-axis, then we're going to have a cone again. Or we're going to have a cone. We're going to have a cone. So this rotates about the x-axis. I always draw this little kind of curved arrow to remind myself where I'm rotating around. So our volume is going to be equal to, I'm going to have, what am I going to have here? Well, if I have a cone, then I'm going to have a disk there. So it's going to be equal to pi times the integral from 0 to 1 of 1 minus x quantity squared dx, right? So, because this, and you can imagine this here, this is your disk. The dx, if we're integrating from 0 to 1, we're going with dx here, and the radius is that 1 minus x, because that's where it hits, wherever, you know, that's the equation of our line there. So this is going to expand to be pi from 0 to 1, that's a 0, looked like a 2, of 1 minus 2x plus x squared dx. So we get pi 1/3 x cubed minus x squared plus x, evaluated from 0 to 1. And we end up with pi times 1/3 minus 1 plus 1, which equals pi over 3. That's our volume. That's the volume of this cone that's created by revolving around the x-axis there. Okay, let's do another one. Okay, for this next one I already drew the graph just to kind of save us some time, but here we're asked to evaluate y equals the square root of x, y equals 0, y equals 4, or x equals 0, x equals 4, sorry, about the x-axis. So we've got our shape here, and if this is rotated about the x-axis, then we're going to end up having our disk right here, right? And that disk is going to be, you know, it looks like you'd kind of get like a little weird bowl shape out of this. So our disk, our volume of this is going to be equal to pi, right? The area of a disk is always going to have pi involved, from 0 to 4 of the square root of x squared dx, okay? This is perpendicular to the x-axis, so we're going to evaluate this with respect to x. So this is going to be equal to pi from 0 to 4 of x dx, which of course is pi times 1/2 x squared from 0 to 4. I'm just going to kind of do this quick. Pi over 2 times 8 minus 0, so, oop, nope, 16. I jumped the gun there. So this is equal to 8 pi, okay? I'll erase that so you can actually see it correctly. 16 minus 0. There you go. So hopefully that makes sense. Let's do a few more examples. Here we are asked to evaluate y equals x squared rotated about the y-axis from 0 to 4. Okay, this one's really interesting because now we're going to go about the y-axis. So from 0 to 4, I'm going to draw this up here from 0 to 4. Well, at 4, we're going to have the point 2, 4. And this would actually, you know, if this rotated, ooh, isn't this cute? You're going to have negative 2, 4. You're going to have that weird bowl again. Okay. And this is rotating, so you're going to kind of have this sort of a shape there, right? And we're now rotating about the y-axis. So if we're rotating about the y-axis, our disk is perpendicular to well, this is the whole disk. Well, yeah, this is the whole disk, I guess. Our disk is perpendicular to the y-axis, so we're going to have to use dy. Well, y is equal to x squared, so x, this value here is still x, right? That our radius, r, is equal to x. Well, x is equal to the square root of y. So our volume is going to equal pi from 0 to 4, because we're going from 0 to 4 here on our y-axis, of our radius squared, which is going to be the square root of y squared, dy. So that's equal to pi from 0 to 4 of y dy, and like math it up, but this is going to be equal to 8 pi, very similar to the last one that we did. Okay, let's do one more example of our disk method here, and then I want to dive into the washer method a little bit. So here, y is equal to e to the x, and we want to revolve this about the x-axis from 0 to 2. So if I've got this, I've got the point 0, 1 here, and this goes up, and at 2, this is at 2e squared, right? And this is going to be our disk. It's going around the x-axis, so our disk is going to be here. And I draw these disks pretty thick, but hopefully you kind of understand that these are, you know, like infinitely smaller and smaller and smaller because we're using integration, right? So if we're using the x-axis, we're perpendicular to the x-axis, we're going to use dx. So our volume is equal to pi from 0 to 2, right, from 0 to 2, of our radius. Well, the radius here, the height here, is e to the x. E to the x quantity squared, dx. So that's going to be equal to pi times e to the 2x over 2, evaluated from 0 to 2, which is pi over 2 times e to the 4th minus e to the 0, which of course is 1. So we have pi over 2 times e to the 4th minus 1. And you can probably just leave it like that. I mean, you could keep writing it simpler if you wanted to, but that's basically all of it is. Okay, so now you've figured out the disk method, so let's talk about the washer method. We don't mean washer like washing machine. We mean washer like a washer that you would use kind of in construction, right? Like, so it's basically just a ring. So the washer method is going to involve two equations, and you're going to actually have to find the area between them. This is why we already found the area between two curves, right? So here we've got a shape, like this is, I don't know, like this is a function, this is a function, and this we can call our r of x, and this we can call our small r of x, right? So the big R of x, well, what's that going to be? That's our outer radius, right? That's our outer radius, and the small r of x is our inner radius. And you can see that these, if we rotate this shape in between here, this like in between shape, we're going to end up having a hole in between, right? That's what the washer is. That's where we create the washer. I actually have an image here that I got off of the internet. Hopefully this kind of like maybe shows a little bit better than what I can draw, but you've got f of x here and g of x here, and if I rotate this around, you're going to get a shape like this, and there's a hole in there. There's this gap in between whatever this shape is that we've created. So we can actually find the volume of these solids the same way that we did using the disk method, but just a little bit extra work, right? So we want to find the volume of the solid formed by the region of the graphs y equals the square root of x and y equals x squared about the x-axis. Well, I've already drawn that here. So we've got our space here, and we're rotating it about the y-axis. Okay? So we're going about the y-axis. We're going to have a space there in the middle. So we need to take our outer radius minus our inner radius, right? So r sub y, I'm going to write this down here, okay? If we are perpendicular to the x-axis, can you see that? You need to solve for y. And if we are perpendicular to the y-axis, you need to solve for x, okay? The cross sections, all right? So whatever your disk is, or the cross section perpendicular. This is important to remember, okay? So here, we're going around this, we're going to be perpendicular to the y-axis, so we need to solve for y. So our large, our outer, what am I saying? Outer radius is this equation, y equals x squared. And our, excuse me, inner radius is going to be this equation here, y equals radical x. Well, like I just said up here, if we're perpendicular to the y-axis, then we need to solve for x, right? So x here is going to be equal to the square root of y, and x here is going to be equal to y squared. Important so that we can actually find this volume. So what's our interval going to be? If we're using dy's here, it's going to be from 0 to 1. I'm just going to make a note of that here to myself. And now I think I'm ready to integrate. So our volume is equal to, we still basically have a disk. This disk just has a hole in it. So our area is still going to involve pi. So it's going to be pi times the integral from 0 to 1 of, well, our radius squared. Well, our radius squared is going to be our big radius, radical y squared, minus our little radius, y squared, squared. I should probably put that in parentheses. dy, right? So that's going to be equal to pi times the integral from 0 to 1 of y minus y to the 4th dy. We can keep integrating that. So we're going to get pi times 1/2 y squared minus 1/5 y to the 5th from 0 to 1. So you're going to get pi times 1/2 minus 1/5, which is equal to 3 pi over 10. Okay. All right, 2 more examples, and then I think we'll be done for today. So, can you see that okay? Okay, beginning of the last 2. Find the volume of a solid generated when the region between the graphs of f equals 1/2 plus x squared and g of x equals x over 0 to 2 is revolved about the x-axis. Okay, what a mess. Well, let's draw this out here. I think it's always helpful to draw these a little bit, just because if you do, I think it creates a better visualization to see, you know, where this is revolving and kind of what it would look like. So there's our y equals 1/2 plus x squared, which is our f of x. And we're going to have something like this for, oops, why did I curve that? Well, ignore that it's curved. I have a tissue here. Okay. So y equals x, which is our g of x, okay? And we're going from 0 to 2. So this is 2 here. And if we're revolving this about the x-axis, then this is going to be our outer, right? Our big R, and this is going to be our inner, our little r. Okay? So, knowing that information, our volume is going to be equal to pi times, well, we're going the interval from 0 to 2. So 0 to 2 of our outer is going to be 1/2 plus x squared squared minus our inner, which is just x squared. Okay? X squared, and I don't know, why do I put all this in so many parentheses, but I do. All right, so anyway, this is equal to pi times the integral from 0 to 2 of 1/4 plus x squared plus x to the 4th minus x squared dx. Those beautifully cancel out. 0 to 2 of 1/4 plus x to the 4th. So we get pi times 1/4 x plus 1/5 x to the 5th from 0 to 2. So we get pi times 1/2 plus 32/5, which is equal to 69 pi over 10. There we go. That's our volume. I didn't draw it very well, but hopefully it made sense. Okay, last one. We are asked to drill a hole through a metal sphere of a radius that has a radius of 5 inches. The hole has a radius of 3 inches. What's the volume of the resulting metal ring? Okay, well, like I said before, it's always nice to draw these out. So if I draw this, oops, my metal sphere would have a radius of 5, right, 0, 5. But actually, I already graphed this on my calculator, so please just trust me. But this has an intersection point at 4, 3, So at negative 4, 3. So if this is the hole here, right? That's the hole that we drill through it. And this is the metal sphere. I guess I could draw the other side if you wanted. But anyway, so here's that big gaping hole. And this is the metal sphere that we're trying to find the volume of that ring that we still have. Okay? So, and this goes around, obviously. So, where are we rotating this around? Well, we're rotating around the x-axis. Okay? We're rotating around the x-axis. And the equation of this, because we're going to need that equation, is going to be x squared plus y squared equals 25, right? It's a circle. So y, in this case, would be equal to the square root of 25 minus x squared. We need that because our disk is, well, that's the equation here, right? So this is radical 25 minus x squared. And this is just 3, okay? So now we can actually use that information to find our volume. So our volume is going to be equal to pi times the integral. Well, where are we going from here? Okay? Where are we going from? If we're using our x-axis, which we are, we're perpendicular to the x-axis, so we can use our x's. We could use symmetry here and use a 2 pi, but I'm just going to go from negative 4 to 4. You should get the same answer. If you don't, you've probably done something wrong. So our large radius here is going to be the square root of 25 minus x squared, and of course that's squared, minus our small radius is just 3, right? Because we're going from here to here and then from here to here. So our small radius is just 3 squared dx. We're perpendicular to the x-axis, so we're going to use dx's. So we need to solve, make sure that we're having a radius of x, right? So this is going to be equal to pi times the integral of negative 4 to 4 of 25 minus x squared minus 9. This should work out very nicely, actually. Pi from negative 4 to 4 of 16 minus x squared dx. Maybe I spoke too soon. Pi times 16x minus 1/3 x cubed from negative 4 to 4. So I get pi times 64 minus 64 thirds. Yeah, I spoke too soon. Minus a negative 64 plus 64 thirds. So that's pi 128 minus 128 thirds, which equals 256 thirds pi. And we actually know our units here. It's inches. We should use them. This is volume. It's going to be inches cubed. Okay, I know that was a really long lesson and a lot of information, but hopefully it makes sense. Any questions, leave them in the comments, and I will see you in class. Bye!